Hello again, this is Tim Baldridge, and we're here for another Clojure tutorial, a set of tutorials actually. Today, we're going to talk about DataFlow. So I did a talk at Clojure West a little bit ago called Core Async in Use, and I mentioned this concept of DataFlow. Now, it's interesting, I realized afterwards that I don't think I've ever actually seen an implementation of this as a library, so I thought we'd build one. It's not an incredibly complex thing to build, but it's more of just theory about graphs and how they work and how to program them. So basically what we're going to do is we're going to build a graph of nodes, right? And these nodes are going to communicate via inputs and outputs. Each node can have multiple inputs and multiple outputs, or no inputs or outputs, right? That like a node that only takes inputs may be a sync node. A node that only has outputs may be a producer node or a source node. And then the nodes in between there transform data. Now this is a graph in which we can have things like loops and stuff. So it really kind of models, you're going to see DataFlow graphs mentioned in tutorials or in conversations about compilers, about things like CSP or Core Async. And we can use this sort of analysis in a lot of different situations. But what we're primarily focused today with is a type of thing where we're flowing data through this graph. And we're actually going to set up the graph once, and then we're going to flow data through it. And this sort of thing can be used for rules engines and query engines and the like. Okay, so let's get started. Obviously, the start of this entire graph is going to be a graph record. It's going to have nodes and links, right? So nodes will be a hash map of nodes, and then links will be links between the inputs and outputs of those nodes. Simple enough. Okay, so now what we're going to do is we're going to make a couple functions. Add node to graph node. And what this is going to do is simply associate into the graph at nodes the ID of node. And in fact, I'm gonna do this a little bit differently because I like this format. Now, people may disagree with me about the proper way to, if it's worth doing the destructuring there, but whatever. I like the way this looks. So we're going to pull the ID out of the node. We're going to associate that into the graph at that location, and the value is going to be node, right? So we have a graph, and we have a way to add things to that graph. Now, these graphs are immutable. Everything we're dealing with so far in this DataFlow graph is completely immutable. Later on, we may add things like parallelism. That'll also be immutable data we're working with. Until we get to stuff like Core Async, we can make these graphs be fully concurrent where the nodes communicate via Core Async channels. But you know what? We'll deal with that when we get to it. At that point, we'll start dealing with mutability and things along those lines. So we'll also have link. So given a graph, given a and a from, go to a port on B. Right? So this is a way of looking at, we have a node, and then this is going into another node, and we can have a from port into the to input of the other node, right? So that's kind of, I like writing the, it's a little bit of a DSL, if you will, but the direction of reading this in English makes sense. So we're going to link A, the output on A, called from to B. Okay, so now we're going to associate to the graph into links, and now this is going to be a nested hash map. So what we're going to do is we're going to say A from to B. Actually, we need to update in here. And I'm not actually sure, come to think of it, that we need this as a hash map there. I think we can actually just do something like this, fnil conj, and we'll put into the set 2 and B. If we need to fix this up in the future, that's fine. But basically what we will be able to say here is that the output of one node is going into the input of the other node, right? Okay. Let's go in the right namespace here. Graph. There we go. There we go. And now let's give ourselves a little bit of a let's give ourselves a node here. Actually, we'll just use hash maps for now. But let's look at what this looks like. So nil and nil will be fine here. So we're going to create a graph and then add node. The node we are going to add ID 42, an ID, let's do A, like that. Add node ID B, ID C. And if we look at our graph here, we see that we have nodes A, B, and C, right? And they're all indexed properly by ID. And then we can link them. Link A. So we're going to link A and the out of A into the in of B. Wrong number of args to the fnil. Oh, yeah, because there we go. There we go. So now the output of this, we can see here we have links A. The out of A goes into the in of B. B out in, let's see, right. Great. Now this is a graph, right? So there's nothing stopping us from doing C out in A, which would create a loop, right? So we have A goes to B, B goes to C, C goes to A, and we have a loop. Great. Perfect. Okay, so that doesn't give us a whole lot, right? I mean, that it's like, great, we can create a graph. There's nothing about this that actually does anything for us. So let's create a simple node, right? The simplest form of node that we can do for this is a map node. We're going to have an ID and we're going to have an F, right? F is the function, and we need a protocol for this. Def protocol inode. And inode is going to have ingest, and we have state, followed by message. So this is a form of message passing, right? Actually, we'll have port and message. So this is a form of message passing, but in this case, we actually tag every incoming message with the port. So if you linked here, you said A, the out of A goes into B, well then the message that any messages that come out of A on the out port are going to be re-tagged and renamed to in when they come in to B. Right? So we'll just do a case. So we're going to do inode on this map, and we're going to do ingest state port message, right? And all we're really going to do here is we want to emit a message that's been processed through F. Now we need to make that function. So let's do defn emit, and Clojure will complain. No, actually it doesn't complain here. Cool. I was thinking of something else. So state and message. And we need port. State port and message. So this will say emit onto an output something, emit this message, right? So how do we go about doing that? Right? Well, it's pretty simple. What we're going to do is we're going to conj onto this state. So we're going to do state update in state outputs. We're going to do port, and then we're going to actually do let's see here, outputs port, and we're going to conj actually is fine in this case, message. Okay, so given a state, and we can see what this looks like, right? Emit, if we have an empty state, and out is our port, and we output 42, we get this, outputs out 42. Now actually I would prefer a vector here, so let's fix that real quick. Fnil well, let's see, conjvec. And this is just going to be fnil. If you're not familiar with fnil, fnil basically says if the first argument is nil, or if, in this case, you could have multiple other arguments here. But if if these arguments are nil, they're replaced with the argument we give it. So we say we really just want to use a vector here. So we'll do conjvec. And when we run that and we run emit, okay, now we got a vector. The reason we had to do that is because if we thread the state here, so we start with state and emit multiple things, we want them in the right order. If this is just conj, it actually inverts the order. So we'd have 3 and then 4, and that's not really what we want at all. We want to maintain the ordering. It really shouldn't matter, but let's not confuse our users more than we need to. Okay, so now we have our outputs, right? So now we can write map, right? Map just says case port in emit state out f of message. Boom. And we have a problem here. It says unable to resolve symbol inode. I didn't evaluate that, I guess, right? There we go. So now we have this map node, right? And we can play around with this and see if it's what we expect, right? So given a state, actually our initial state here is going to be map ID A, and then increment is going to be our function. We can ingest into that 42 and in on the import, and there we go. What we get as an output here is outputs out 43. Great. So you can see here we're building these immutable nodes, right? And if we could ingest multiple messages, and in each time it's just appending new stuff to our state. Okay, so now it is helpful to make ourselves a system that will automatically assign IDs, right? So let's do next ID. And we're going to let a atom 0, and so this just creates an atom, a inc. And each time we call this function, we're going to get a new ID. That's going to be a unique ID, and it will reset whenever we create a new, whenever we reevaluate this namespace. But now we can write something like this: map node f, and we do map next ID and f, right? So now we can create map node inc, and each time we call this, we get a new ID. Excellent. For our use case, I think we'll ignore that part of it, though. I think for now we're just going to replace these. We'll keep working with this tutorial. Map ID of A, inc, map B, square, map C, and dec. So actually, instead of this, we'll do, this is a fantastic looking function, by the way. Look at that. It's like there's like nothing that makes sense. But basically, we're just going to square the value that we get, right? So we chain these all together in this way, and we'll leave out this last link. So we'll take a value in and increment it, and then we'll square it, and then we'll decrement it. And when we throw this all together, sure enough, look at that, we got our graph. Now, if you're saying, wait a minute, this doesn't actually do anything, you are absolutely right. This does squat so far. I mean, we've created a data structure, whoop-de-doo. In the next tutorial, we'll talk about how we actually execute this graph. It's pretty simple. In fact, if you sit down right now, you could probably figure it out, but we'll talk about it next time. Thank you.